All right, so we're looking at counting 101 here. And the first question is, how many integers are there from 6 to 31? And this might seem like a really basic question. I guess it kind of is, but there's a little bit of a trick here that could catch you if you're not paying attention or if you haven't thought about this before. Um, so if you just want to subtract, you're going to get it wrong, right? So if you want to pause here and think it through, go for it. If you take 31 minus 6 and get 25, that's going to be close, but the problem is, since this is inclusive, since we're including 6 and 31, including 6 is the issue. When you include the first number, when you subtract, it doesn't really count the first number, right? If we take 31 minus 6, that gives you all the numbers after 6 up to 31, all the integers, that is. So what we really need to do is take 31 minus 6 and then add 1. And so we're actually going to get 26. And without actually just counting all these, you could do it with a smaller range. Like if you did like from 8 to 10, right? Well, 10 minus 8 is 2, but 8, 9, and 10. Boom, there's 3 of them, right? It's kind of like the idea of a fortnight in the UK, if you've ever heard that term. A fortnight means 2 weeks, but it means like 2 weeks from, say, a Sunday to a Sunday, including both end days. So it's actually 15 days, right? So even though a fortnight, we might interpret it as 2 weeks, in the US we say 2 weeks is 14 days, right? We go Monday through Sunday and then Monday through Sunday again. But in the UK, when they say a fortnight, they mean from Sunday through Sunday, including that start day. So it's really the same idea there. All right, let's get a little trickier here. And what if you want to know how many multiples of 3 there are from 37 to 605? And I don't know why I spelled this 3, but everything else I wrote the number. But oh well. And then how many multiples of 5 from in that same range, 37 to 605? And then how many multiples of 3 or 5, but not 15, which is of course 3 times 5, from 37 to 605. So another way to say that, how many multiples of 3 or 5, but not both, right? Like an exclusive or. All right, I'm going to give you a chance here to pause and try these if you'd like. Okay, so let's go through that first one. And if you were stuck, or if you realize something when we do the first one, then you could pause and try these other ones again before we go through those. It's tempting to just subtract here right away and try to divide by 3, but I'll caution you there. It's got some problems, right? If you want to subtract, does it matter? We're looking at multiples of 3, so does it matter how close these are to a multiple of 3, right? Like 37's 1 more than a multiple of 3, and 605's 1 less than a multiple of 3. So like when you go from 37 up to 605, you're 2 away from a multiple of 3 to get to 39, right? And same thing on this one going the other way. To get to 603, you're 2 away. So when you subtract, you're going to have an extra 4, right? Is that going to skew your answer? And then, what if instead of that, what if these were both multiples of 3? Then you'd want to include the starting one and the ending one, and you wouldn't have those extra 4 added in. So I don't know if there's a consistent approach if you just subtract first and then divide by 3 and then think about adding 1 or not, right? So instead, I think we might need to think about those nearby multiples of 3 first, right? So for example, you could go from 39 to 603, right? And so you could subtract those, and we'll divide by 3 first maybe, and then subtract, and then do the counting principle we did on the last problem, right? Where you add 1 at the end, right? So if you divide by 3 here and you get 13, and you divide by 3 here and you get 201. 201 minus 13 is 178, or is that right? I'm sorry, 188, geez, 188. And then if you add 1, 189, it should be the right answer. Now, we just did this in class the other day, and the student suggested, okay, what if you if you wanted a formula, so you didn't have to like, because we just knew what the multiples of 3 were, right? But what if the numbers weren't so obvious, or what if we want to generalize this? What if we took 37 divided by 3, and we take 605 and divide by 3? You know what, I'm going to put the 605 first because it's the bigger one. And we subtract those. And the issue is the 605 divided by 3 is going to be that 201, but now it's going to have that extra 2/3, right? The remainder of 2. And 37 divided by 3, that's going to have a remainder of 1, because it's 36 divided by 3 is 12. And, you know, so what if we could kind of get rid of the remainders, come up with a way to do this? And so a student in my class the other day suggested, okay, what if we use the greatest integer function? So these brackets mean the greatest integer less than or equal to this. So it's really just a way of, you round off, you round down, right? So you round down to the nearest integer. If it's already an integer, if this is already divisible, then you just get what you get. But if we have a remainder of like 2/3 on this one, we just drop the remainder. So we don't round up even though it's 2/3, we round down. Because we don't really want to go to 606, right? That's not in the range. Okay, so that works. And then this student suggested, okay, what if we do the opposite on this one? What if we round up? Because we don't really want to do 36, it's not in the range, we want to do 39. So this is the least integer function. So this greatest integer function, that means the greatest integer less than or equal to that value. It's called a floor function also. It's called the greatest integer function, the integer function, the floor function, or step function. These are both step functions. This one's the least integer greater than or equal to. Same idea, opposite direction. Okay, that would work, because now we're looking at, this gets us that 201, and this gets us that 13, right? Here we round up, so it gives us 13, right? Because 37 divided by 3 is 12 1/3. So the least integer greater than or equal to that is 13. So then we still have to add that 1, right? So let's do the plus 1, and this formula would work. So now if you want the multiples of k from a to b, multiples of k from a to b, this is a system that'll work, right? We could do b divided by k and take the floor function minus a divided by k and take the ceiling function, and then plus 1. That works. And we could probably simplify it a little more if we, we could make these both floor functions, right? And if you did that, well, you gotta be careful again, right? Because the problem with switching this to a floor function is if it's exactly a multiple of 3, it doesn't change if you do floor or ceiling. So I think this might be the most direct and intuitive way, I think, to do it, right? Because the idea is we want to round this one down, right? The bigger one down to the nearest multiple of 3. And we run around this one up to the nearest multiple of 3. That's what we're doing here, right? Okay, so you could use the same idea here. So if you wanted to pause now, you could. And I'll go through it now. So if we take 37 over 5 and take the least integer function, or sorry, the greatest integer function. It was the least integer function. That's the littler number, right? We're also going to take 605 over 5, and here we'll take the greatest integer function. So this other one needs to be fixed. Ooh. Okay. Subtract and add 1. We should be good to go. 605 divided by 5. Well, 5 goes into 100. 20 times. So that's 120 and then one more. So 121, and that's exact. So we don't need to round it, it just is. It's 121. And then 5 goes into 35, of course, 7 times. So this is 7 and change, right? It's got a remainder, but now we round up, so that's going to be 8. And then plus 1 to maintain equality. And so it's 122 minus 8 is going to be 114. This one up here was 189. Okay, so we can use the same principle down here now to find the number of multiples of 15, right? We can do 605 over 15 minus 37 over 15, round that one up, plus 1. And so let's see, 15 goes into 64 times, so it's going to go into 640 times. So that's going to be 40 and change, right? 40 and 5/15ths. But we're rounding down here because it's the greatest integer less than or equal to, so that's good. And then 37, excuse me, divided by 15, that's just going to be 2, but then and change, and we're going to round up, so it's actually going to be 3, and then plus 1. It's what, 37 plus 1, 38. So there are 38 multiples of 15 in here. And what we want, though, are multiples of 3 or 5, but not 15. So now we get into one other idea here. And maybe you thought to do this. You picture a Venn diagram. It's kind of a set theory thing. And you have multiples of 3 for one of these, and multiples of 5 for another. And then you have multiples of 15 in the center, right? Because that's both 3 and 5. So in the center you're going to have numbers like 15 and 30 and 45 and so on. Out here you're going to have 3, 6, 9, 12. Not 15 though, because that's over here. It's still in this circle, but it's also in the other one. 18 and so on. Over here you're going to have 5, 10, well not 15, that's over in this part. 20 and so on. So the idea is we want to take all the multiples of 5 and all the multiples of 3 and add them together, but then we want to realize that we don't want the multiples of 15 to be included. So first of all, we're counting them twice, right? If you take 189 plus 114, we're going to get, it's at 303. And then the problem is, first of all, we've already, not only have we counted the multiples of 15, we've actually counted them twice, right? We counted the multiples of 15 in here 2 times because we counted them with the, they're in here with the multiples of 3, and they're in here with the multiples of 5. So we have to subtract them. We actually want to subtract them out twice because it says but not 15. We don't want them at all. So we're going to subtract out 38 times 2, which is actually 76 from this. And that's going to give us, what, 227, I think. And that's our correct answer here. So that's the answer to that question, to that last question there. All right. I think I've got, well, yeah, one more for this setup here. We're going to look at one more property now here for counting. And we're looking at something called the multiplication property. And this property says that if you have A ways of doing one thing and B ways of doing another thing, you want to know the total number of ways of doing kind of both things together, you multiply, right? So real quick, if I have 3 pairs of pants and 4 shirts, how many outfits, right, if I'm just talking pants and shirts, are possible? And you know, this is, you've probably done this before with like a tree diagram, right? Like here's pants. I have 3 possibilities for my pants. Maybe they're beige and gray and black. And then I have 4 shirts, and with each pants I can wear any of the 4 shirts, right? So I get 4 branches off of that one, and I'm also going to get 4 branches off of that one, and I'm going to get 4 branches off of that one. So altogether there's 12 different routes, right? 3 pants times 4 shirts, 12 combinations. Okay? So with that in mind, it's a good time to pause if you want to try these next 2 questions. Okay, let's look. So if you're going to have 3 letters and 4 numbers, the question is how many different license plates are possible, and if there's no rules, then you can reuse letters and you can use any combinations you want. You know, I didn't phrase this very clearly though. I should have said 3 letters and then 4 numbers is what I intended, but that is different than what I wrote. So if it's 3 letters and then 4 numbers, we're going to have, well, 26 possibilities for each letter, right? And then 10 possibilities for each integer, right? Because 0 through 9. And so we're going to have 26. You multiply it all out, right? It's the same as up here, except now there's 7 things to multiply. You have 26 times 26 times 26, or 26 to the third, times 10 times 10 times 10 times 10, so 10 to the fourth. However, if I didn't have the and then, well, we have an interpretation thing here. What if it had to be the 3 letters together and the 4 numbers together, but you know they could go in either order? If it could go numbers then letters, then all you have to do is consider doubling this, right? If you put the numbers first, it's just a different ordering of all of these same groupings, right? So you could have like AAA 1 2 3 4. You could have 1 2 3 4 AAA. That's for each combination of 3 letters in a row and 4 numbers in a row. That's just that, right? So it would just be 10 to the fourth, or sorry, it would be 26 to the third times 10 to the fourth times 2. Now, what if, since I wrote it wrong to start with, what if there were no stipulations at all? What if they could be any 3 letters and any 4 numbers in any order? Well, then, once you find, and this is more advanced, this will be in a later video, but once you find the 3 letters and the 4 numbers, the total number of combinations of those, then you need to consider all the possible placements. So what you could do is, if any ordering of letters and numbers is possible, but if it still has to be 3 letters and 4 numbers as it was written, then you would take this total, this 26 to the third times 10 to the fourth, and then you'd have to multiply it by 7 choose 3, or 7 choose 4. Basically, you're taking the 7 slots, and you are finding how many different ways you can pick 3 of the 7 slots to be letters, and then by default the other 4 would be numbers. So it would be 7C3, this is combinations, times 26 to the third times 10 to the fourth. I'm not going to go deeper into that right now because that's really kind of beyond the scope of this first video, but again, since I miswrote the question to start with, I thought I'd just address it in case you were wondering, in case you had an idea. Alright, now, back to the original problem, how it was supposed to be written, 3 letters and then 4 numbers. But suppose somebody goes through and says, hey, okay, you can't have, I'm sure you can all think of some letter combinations that might not look so good, right? Maybe you wouldn't want it on the back of your license plate, on the back of your car. Or maybe you would, I don't know. But they removed some. So suppose they remove 49 letter combinations. And I bet whatever 49 they come up with, we could all find even more than that if we're creative. But what does that do to it, right? Well, again, if you have letter, 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 then number, 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 number. You got your 26 to the third letter permutations that are possible, right? We're just taking away 49 of them. So it's going to be 26 to the third minus 49. That's the total number of allowable letter permutations. And then for the numbers, same deal. It's going to be 10 to the fourth is the total number. And then there's apparently a few numbers, combinations that are profane or whatever. And so we're going to subtract out the bad ones. Right? And that's what we'll get. So that's all you got to do. I'm not bothering to evaluate these because that's not really the point. It's the tough part's the setup. I'm sure we can all put these into a calculator. Okay, so that's it for this video here. This is what we did in class the other day, and I'm going to build on this with another one and try to get a series of Combinatorics videos that can get us comfortable with permutations, combinations, distinguishable permutations, and some other counting things that will come in handy with some of the stuff we're going to look at. All right.